Welcome to this lesson on calculating the abundance of isotopes using algebra. This is something that isn't always covered at school, and it might be that you didn't actually realise you needed to know how to do this. If you come across one of these questions without being shown how to do it first, it's likely that you'd struggle a little bit. But these questions are actually quite straightforward, and by the end of this lesson you should be feeling pretty confident at tackling them. Here's the learning outcomes for this lesson. We'll start by revising the formula for calculating relative atomic mass from mass spectrometry data. We'll then learn how to use this to calculate the abundance of more than one isotope using algebra, and we'll learn a simple rule that will make all this that little bit easier. So let's have a look at the equation for calculating the relative atomic mass using mass spectrometry data. The relative atomic mass is equal to the sum of the mass times the abundance of each isotope of an element divided by the total abundance. And remember, we calculate the total abundance just by adding up the abundances of each of the isotopes. Now, I'm hoping that this looks familiar, but if not, you need to take a look back at your school notes or your textbook to see what you've missed. So this equation is going to be important for our lesson today, but it's also important for the topic of mass spectrometry in general and for other calculations that you might do. Now for us today, for this lesson, we're not going to use this equation to calculate the relative atomic mass. Instead, we're going to use it to calculate the abundances of two isotopes. Now if you needed to calculate the abundance of just one isotope, you could easily do so by rearranging this equation to make the abundance of the isotope that you're interested in the subject. If you need to calculate the abundance of two or even more isotopes, you've got a little bit of a problem because you've got more than one unknown variable. That means you're going to have to use algebra to solve that problem. Now we'll have a look at an example of how to do this, but before we do, we've got a rule to learn. And the rule that we're going to learn is that the total abundance is 1. Now the reason that this is useful is because if we make the total abundance 1, we can simplify that equation a little bit, because if the total abundance is 1, you wouldn't actually bother dividing by 1. So that means we can simplify the equation and remove that, so we're left with the relative atomic mass is equal to the sum of the mass times the abundance. Now another reason why this is useful is because if you make the total abundance 1, then each of your abundances for the isotopes will come out as a decimal. Now that's good because if you get it as a decimal first, you can go on and use it to work out whatever else you need from there. So if you needed a ratio or if you needed the percentages, for example, then you can do that very easily. So now we know this rule, and now we have a simpler equation to work with, let's apply it to an example. The example calculation we're going to look at first is asking us to calculate the abundance of the two isotopes of boron. So boron has two isotopes, boron 10 and boron 11. The relative atomic mass of boron is 10.8. And if we want the abundances of the two isotopes, remember we're going to use this equation. If we take a look at this, we can see that we actually have a fair bit of the information we need already. We have the relative atomic mass of 10.8, and we have the mass of each of the isotopes. We have boron 10 and boron 11. What we don't have is the abundance of each. Now that makes sense because that's what we're trying to calculate. But if we're going to use this equation, we have to have something to put in the equation to represent the abundance. Now, this is where our simple rule, that the total abundance is 1, and this is where the algebra come into it. So let's see how we can use this. So to represent the abundance of boron 10, we're going to use x. And that means, bearing in mind the total abundance is 1, the abundance of boron 11 will be 1 minus x. If we take those two ideas then and put them into our equation, we end up with this as our algebraic expression. So we're left with 10.8 equals 10x, so 10 being the mass of boron 10 and x being its abundance, plus 11 times 1 minus x. 11 being the mass of boron 11, 1 minus x being the abundance of boron 11. So now we have our algebraic expression, we need to solve for x. To do that, we'll follow 3 steps. First step, expand the brackets. Second step, we'll combine the like terms, and that will be the x's. Third step, simplify and rearrange to get x. Now don't panic about this. If you're a bit rusty with algebra, definitely make a point of going back and revising simplifying equations from GCSE maths. But we're going to go through this example together and hopefully it will start coming back to you. Let's follow our 3 steps then and calculate the abundances of the 2 isotopes of boron. Remember, we have this as our algebraic expression, and the first thing we need to do is expand the brackets. So we do that by multiplying everything inside the brackets by the number outside. So that means we need to do 11 times 1, and it means we need to do 11 times minus x as well. If we look at that then, we can see that we have 10.8 equals 10x, and so we haven't done anything with that side of the equation yet, but plus 11 minus 11x. So the plus 11 comes from the fact that we times the 11 by 1, and then the minus 11x, we times the 11 by minus x. Now we need to combine the like terms. So the 2 like terms we have are the 10x and the minus 11x. So if we do 10x minus 11x, that gives minus 1x. So we can say rather than minus 1x, we can call it minus x. Now this is where we are now. You can see the equation's getting much simpler. By combining the like terms, we have 10.8 equals minus x plus 11. Next thing we need to do is simplify the equation and get x. You can see the problem is that we have minus x on the right hand side plus 11, so we need to get rid of the plus 11. How we can do that is by subtracting 11. But remember, whatever we do to one side, we need to do to the other. So we need to now subtract 11 from both sides. So if we subtract 11 from both sides, that will leave us with minus 0.2 equals minus x. So we're almost there. You can see we have a minus on each side. The 2 minuses will cancel out then. So that means that x is actually 0.2. And we've done it. We've got x now. But we haven't actually answered the question yet, because we wanted the abundances of the 2 isotopes of boron. So we have x. We need to then make sure we go on and actually answer the question. So to answer the question, we need the abundances of the 2 isotopes of boron. Now remember, the abundance of boron 10 we said was x, and the abundance of boron 11 is 1 minus x. Now x is 0.2, as we've just worked out, and the abundance of boron 11 will be 1 minus 0.2, which gives us 0.8. So there we are, we have the abundances. We've now answered the question. If the exam question asks you just to give the abundances and you get to this point where you've got the decimals, then you're done. That's absolutely fine. You can leave it like that. But some questions might ask you for the percentage instead. And if they do, you've got a little bit more work to do. So to calculate the percentage abundance, take the decimal abundances that you've got there and then just multiply them by 100. So for boron 10, 0.2 times 100 gives us 20%, and boron 11, 0.8 times 100 gives us 80%. Now we're going to have a look at some more examples of this, and I'm going to get you to have a go by yourself in a minute, but let's just recap on how we approach these questions. I'm going to give you 5 pointers, and I want you to either write them down or take a picture with your phone so that you've got them to look back at, and you're going to apply these to some more questions. So the first pointer, remember the total abundance is 1, that's our important rule. Secondly, the simplified equation we've been using, the relative atomic mass is equal to the sum of the mass times the abundance. 3, whenever you have an equation that involves calculating the abundance of 2 isotopes, make the abundance of one of them x and the abundance of the other will be 1 minus x. If you have more than 2 isotopes, you've got a little bit more work to do, but we'll worry about that later. Then solve for x. Finally, just check that you've answered the question. So if they ask you for the percentage or they ask you for a ratio or something, make sure you convert it into that. Now, when you're ready, move on to the second video and we'll look at some examples.